Oi, what is good, y'all? We are back with the Layernorm lesson, right? This is my second time recording this, so bear with me here if I'm a bit frustrated. Should go well though this time, fingers crossed. What we're learning today, we're going to use Layernorm as the function we do it with. We're going to learn backwards passes, right? How to actually write one, as well as connecting the backwards pass to PyTorch's actual graph. And we're going to learn how to reuse intermediate values from the forward pass in the backward pass and why that's good. We'll also learn how locks and atomic operations work and what they are, I guess, as well as the sometimes benefits of two sequential kernels can be faster than one single kernel, right? Which is counterintuitive, but sometimes it is better to have two separate kernels working together, one after the other, than it is to try and do everything in one kernel, right? As always, this is a video on the actual parallelization schemes, the actual architecture stuff, not on the math. So on the backward pass stuff, we are not going to go over why this is the derivative. We're just going to write the equations that we get the derivative with. If you want derivative lessons, go to a calculus class. That's a prerequisite here, right? But we're going to focus on the actual parallelization scheme on our GPU. First off, just pasting in our imports. Then step one, always create our test. We're going to take as inputs the actual shape, as well as data type, epsilon, which is a very small value designed to help us avoid division by zero errors later on in the actual Layernorm part. Defaulting to device, of course. To create our data, we want data that is actually needs to be layer normed, right? So we're going to say our tensor x is going to be shifted by -2.3 and scaled by 0.5, and the tensor itself will be just a normal distribution of the given shape m comma n. Then we need not only the actual input data, but also our weight and our bias. These will be, let's make them a uniform distribution to keep them small, of length n, aka our embedding dimension. This is going to be entry-wise multiplied by our actual input data. And for this one, we're going to say requires grad equal to true, unlike the previous one, unlike the x. And the bias is the exact same. And then after we actually initialize x, we then have to say x dot requires grad is true. This doesn't really matter for the testing, but doing this, I believe, if I remember correctly, will matter later for the benchmark, I think. Reason being that if you don't do this, if you actually have requires grad equals true be inside or inside the actual initialization, then you're going to be calling kernels right here for this multiplication and addition that then would get confounded into the benchmark, right? So this actually, I think, is unnecessary for the test, but I'm going to leave it in here anyways. I think I had it just by copy and pasting earlier, so it's not going to break anything. But for the benchmark, we wouldn't want to confound our actual speed results with that of whatever these two kernels that PyTorch implements are. Then we go ahead and run the function we have not made yet, the Layernorm wrapper, around our actual kernel. For sake of staying consistent with PyTorch syntax, I did this here as I actually included the shape of our weights and bias, even though we're not going to use it in our wrapper. Input our weights, our bias, and our epsilon. And then that is our Triton version. And then our reference value from PyTorch will be torch.nn.functional.layernorm and same inputs. I don't know why PyTorch needs the actual shape of the weight and bias matrices, but it does, and we're going to stay consistent with that. And then I don't think data type should be an issue, but for some reason in my earlier code that I'm referencing off screen, I did make sure this got pushed to the right data type. Then just a simple torch.testing.assert close, and we're going to go for tolerance this time, 1e -2, and no relative tolerance. If it gets through all that, We can print out a pass to the forward pass. And then let's go ahead and do our backward pass test as well. So we are going to do a dot backward. Oh, we first need to do what's our actual gradient though, right? So dl dy equals, let's say 0.1 times torch dot random normal distribution like x, same shape obviously because the output has the same shape as x. Then we're going to back propagate that, dl dy, retain graph equals true. Two notes here. For my notation of any derivatives, I am going to always clarify that it is with respect to the loss function, dl dy. If you were to write this, it would be a fraction dl over dy. And also the correct term would actually be partial L over partial y. But I don't want to write the word partial. D is mathematically incorrect for all of you math people nitpicking, but for a CS project, close enough. I believe in the original Triton docs, what they did is they just said things like dy. They had the dl was implicit, which I was not very fond of, because at that point we're getting multiple degrees away from the actual correct notation, but whatever. We backpropagate on our Triton version, and then those gradients should now be attached to x, weight, and bias. We can grab them, the LDX of the Triton run. Same thing with weight and bias, equals, and we're going to remove them from the actual graph so that we can use the same graph again. Notice we have a retain graph equals true here. Usually when you backpropagate, PyTorch will forget all of its pointers of the graph and it will just delete it all because it doesn't think you'll use it again and it wants to save memory. But we know we're going to use the exact same actual graph connections later. So we are going to retain our graph to be used later. .grad.clone for underscore in x, weight, bias, right? That just grabs all of those and the clone disconnects them from the actual graph, copies them effectively. And then we can set the actual values of these gradients equal to 0 by setting them to none. PyTorch by default doesn't actually hold a tensor full of zeros or anything in the gradient. It actually by default holds a bunch of none values, right? Not tensors. And then we can do the same for our reference PyTorch version. We do backward, dl dy, retain graph equals true. I don't think we need to use this a second time. I think this is a pretty useless right here, but who cares? It's not hurting anything. And I don't want to change code I've already written in the moment during a tutorial, of course. dldx reference, dldw reference, and same with B. Go ahead and copy that. And now we can do our actual comparisons, which are the same as our earlier comparison, except we do 3 of them, 1 for each gradient. Oops, that did not work. There we go. And if it passes through all of that, we can print out passed the backward. That is our test all finished. Next, we are going to build our wrapper. This is the new thing here. The first new thing we're going to see is our wrapper is actually different from prior lessons. In prior lessons, it was a simple Python function. Here, however, in order to connect your actual kernel to PyTorch's backpropagation graph, what you have to do is make a class, Layernorm we'll call it, and its parent class is torch.autograd.function. Very important here, right? This is how you tell PyTorch we are going to create functions that need to be a part of the backprop graph. Our first method, we label it with static method, def forward, and this will be our actual wrapper for our forward pass, and we'll have a separate one, also a static method. This is just, you always have to prepend in front of these two things. Don't think too much about it. And def backward, right? And now let's actually fill in the forward first. It is going to have as entries ctx. We're never going to actually input that. That is a little object that PyTorch knows how to use and that is useful for us that we'll see how later. Our actual main input x, the input tensor, then that normalized shape, that was our parenthesis n right here. We're not actually going to use this, but they use it in the original PyTorch version, and just to keep syntax consistent, let's go ahead and leave it in there. Why not? Then our weight, and our bias, and our epsilon. Now to get the shapes out of this, in the test, we actually define m as just a single integer, but we're going to make this a bit more general in our actual forward wrapper. Is it's going to be x.reshape, -1, x.shape, -1 dot shape. Think about it for a second. What this does is if x actually has many different dimensions, for example, batch head sequence, and then embedding dimension, for example, anything that's not the last dimension, it just combines all into one, because Layernorm does not care about your preceding dimensions, and it labels them all collectively as m. And then we are going to pre-allocate tensors, first up being the output, which is the same shape as the input x. Second up being mean and reciprocal standard deviation values. We're going to not just calculate those inside the actual tensor, we're going to actually save them back to DRAM so that we can use these same tensors later in the backward pass. Let's go torch.empty, and it is of shape m, because we want 1 for every single row, right? And then dtype. Generally, for any intermediary tensors, you probably want accurate numbers, so float32. And we are trying to match PyTorch's own values, and PyTorch does do float32 here. Otherwise, I think you would probably get, you might get errors. You might be closer to not getting any errors, but I think you probably get errors if you did float16 right there. And then the exact same thing for RSTD. Now, I want to say it was last lesson maybe where we learned how to auto-tune. Maybe it was 2 lessons ago, how to actually get efficient values for all of our meta parameters. We're not going to do that here. I'm going to do just a quick little heuristic. Max fused size equals 65536. If you want to improve and speed up this kernel, you can by switching over to auto-tuning. X.element size. What this is saying, this number is the number of, this represents 64 kilobytes. And we are saying, okay, how many bytes are in a given element, in a given entry, in a given number of x? If x is FP32, that would be 4. And we are saying, all right, the maximum number of entries that we can fit into SRAM, if we assume SRAM has 64 kilobytes, would be this maxed fuse size then. The assumption of 64 kilobytes is a conservative assumption. This will be like an old small GPU will have 64 kilobytes. If you go to like, I want to say the 4060 Ti I'm on, I want to say it has maybe 98 or 100 kilobytes actually, but this is just a conservative heuristic to hopefully allow this kernel to run on any GPU, but not have to actually do all the hyperparameter tuning and whatnot. And it's just another example of how you would do a heuristic for sake of examples. Then we say block size equals min of max fused size, or Triton dot next power of 2 around n, right? So what we're saying here is the actual block that we're going to load into SRAM with one given program at once. At biggest, it can be max fuse size, and that will mean one program per SM, right? But at smallest, let's just choose the next power of 2 above n, above our embedding dimension n. And then if n is greater than block size, raise runtime error. This Layernorm doesn't support feature dim greater than equal to 64 kilobytes is what we're saying. You could make a better kernel that does support that and everything. We're going to keep things a bit simple and hopefully more efficient within the limited context of inputs that do meet this criteria, right? More heuristics happening here. Our number of warps is going to be min of max of block size divided by 256, or 1 or 8, right? read that through in your head if you need to for a second. It's nothing too crazy. It gets us a value of number of warps that is between 1 and 8, basically. Nothing too crazy there, and it's a heuristic. It's not necessarily very efficient or anything. I wouldn't read too much into this. Again, you should probably auto-tune if you want the ideal value for your GPU, or you should get, as we did in, I want to say it was the second lesson maybe, the actual specifications of your GPU and do the math to figure out ideal number of everything, which this tutorial series is not enough to teach you how to do that necessarily, but again, just go auto-tune kind of thing if you want an actual faster kernel than what we're going to do here. Now, Layernorm forward, this is the actual kernel call, right? Notice we have not made a launch grid yet because our launch grid is so damn simple. It's just M. Every single row of the input matrix gets its own program. And then our input tensor is X, output tensor Y, our weight, our bias, mean, RSTD. And then for our integer values, we're going to grab the stride of X. And notice that weight and bias, we're assuming that the inputs are all contiguous, basically, roughly, a little bit. At least weight and bias are so simple, I'd be surprised if they were reshaped or anything. We know Y is contiguous because it was built, we made Y, same with mean and RSTD. So we're just going to grab the important stride of X, this should be a 0 actually, the important stride of X, which is stride along that M dimension. This actually maybe should be a -2. I'm not going to think about it too much. It works with the current code. I'm tempted to think right now that if we did have a bunch of preceding dimensions, then this 0 might break. If so, if you were to input a bunch of preceding dimensions like batch, head, sequence, whatever, on top of your actual normalized dimension, go ahead and try this being a -2 instead. That might make more sense off of my head, but I could be wrong there. I'm just noticing potential little errors in the tutorial as I see them, because we did not obviously build this to be robust. This is just meant to show a few specific concepts and not really be a production ready kernel or anything. You should be able to check your own edge cases and everything on your own is the hope by combining the lessons from all of these tutorials. So our meta parameters, block size equals block size. We already defined that up above. Same thing with number of warps, right? And then we're going to run that kernel. It's going to put the correct output of our Layernorm and our affine transformation into Y. And then we want to save some data for the backward pass. What we do is we use that input, that CTX, right? This would be useful for that. The CTX is an implied input. Notice how here when we called Layernorm, we didn't actually put a CTX in or anything for that. We just went straight to X. CTX is implied with our torch.autograd.function, and it knows how to handle that. All we have to do is say, okay, if we want to save any data for the backward pass, then we can do so by just, first off, tensors, throwing them into here. We're going to save all those, and then that is for tensors. This is the save for backward method, right? Oops, nope, I don't know what okay. Whereas if you want to save just integers or floating point values, you just do it this way, right? Just give it a new little object or a new little whatever you call it. And then same thing for epsilon. And finally, we can return our output Y. And that is the wrapper of our forward pass. There's not a whole lot to learn on the forward pass. Honestly, we've learned a little bit so far, looking at CTX, for example, and some stuff like that. But we're going to go ahead and write our forward kernel first, I think. That way, when we do the main part of this lesson, the backward pass, we're doing it all at once. So our forward, Triton.jit, def Layernorm forward, right? We're going to get our pointers to our matrices, pointers to the first values of our matrices in memory, right? Stride we put in should be along that M dimension, N value in the epsilon, then our meta parameters, block size, TL.constant expression is a meta parameter that we define that does not have an actual default value in Triton, therefore we have to put it right here. But our number of warps meta parameter, Triton actually always has that and always knows what that is, so you can either choose to specify it or don't. We did choose it right here, but you do not have to specify it again You do not have to specify it again here in the arguments unless you plan to use it, and we do not. Now, our PID, we're going to call it row, since after all, our launch grid is split up, just every single PID is its own row, right? Every single row gets a PID. And we're going to move our pointers to the correct row using our stride. Same thing with Y, right? I'm going to explain the mean one a bit more, and then we'll skip mostly past and like speed through the variance and RSTD one. But we create an accumulator equals TL.zeros, block size, and dtype equals TL.float32. You usually accumulate in a higher data type than you actually want to store in. For offsets in range 0, n, block size. So it looks to me, I'm looking at my code right now, it looks to me like what we're doing here is if our block size is smaller than n, then we will actually we will move down the, the embedding dimension of our matrix n, right? We did earlier say here that we're going to assert that cannot be the case. I suppose you could probably remove this line and have this work. I'm just seeing this little inconsistency at the top of my head. This kernel works, but I think it probably actually does support more than 65 kilobytes in memory. However, I do think what happens here is that you end up with, if the size is really big, if you actually have a very big n and it's bigger than your actual SRAM size that we assumed here wrongfully to be 65536 kilobytes, then it'll be relatively slow. It's a lot better if we can just have every PID be one row and run once, meaning that this for loop only has a single iteration for offset, whereas if it is the case that block size is smaller than n, which you could make happen by just, I suppose, removing this, right? Then it would, in my mind, be a bit of a waste. There's probably better ways to parallelize across this. But again, the forward pass of this kernel is not really the point. We're just going to get it out of the way so we can have it. The point of this kernel is to be efficient is the backward pass. At the end here, we're actually not even going to benchmark the forward pass. For all I know, it's going to be very slow. We're going to only benchmark the backward pass because that's the important one. That's the one that we actually have the big lesson for today. Columns is offset plus TL.A range, 0, block size, offset under this criteria right here should just always be 0. There should only be one iteration of this for loop. So calls should always be an array of 0 to block size. And then our x values equals TL.load, x pointer plus columns. And that grabs the correct values from x. Hopefully, remember, x pointer was already moved to the correct row up here. And then we want to mask out. We can actually do the mask within here. We can say calls less than n, which, remember, we have that block size is just the next power of 2 above n, so anything between n and its next power of 2 will get masked out. And then those values can be put to 0. And then I believe we might be storing x in FP16. We haven't actually determined it yet. We have not determined what we're storing x as. But if we were to store x as an FP16, then right here what we would do is we would change it to TL.float32. If it already is float32, then it shouldn't really matter, but I believe later in the actual call of the test, we're going to define x, its input, as FP16 probably. So then we say sum accumulator, right, plus equal x, the x values, right? So we are probably just doing this once. We honestly, if we take our assumption of the block size and everything here and supporting a maximum size, we could remove this whole for loop, but it looks to me like instead this for loop is more general. We could, if we wanted to, remove this criteria right here, and this should all work. And then this would allow us to actually not parallelize within the sequence dimension, within the embedding dimension, but take our PID and move through the embedding dimension, right? Sorry, it's a bit confusing. This code is a bit more general than I first realized, but it shouldn't matter. The forward pass is not the important thing. Where the backward pass later is the actual bulk of the lesson plan. TL.sum, sum accumulator. The only axis it has is 0, and then we sum everything up, and then we divide by n. That gives us our mean value, right? And then for reciprocal standard deviation, I'm going to, I think, just speed through this. Accumulator. Same deal here. It looks general enough. This for loop right, right, it looks general enough to actually parallelize, not parallelize, but like for loop within the embedding dimension. But we did have an unnecessary assertion earlier in the wrapper that means we're never going to actually have to do more than one iteration of this for loop right here. And it's reasonable because even 65 kilobytes or 64 kilobytes is pretty big. I wouldn't actually expect in any test case scenario simply that we're doing just for tutorial's sake to actually put in a bigger tensor than that. You could make this all faster if you wanted to by either keeping this criteria and removing the whole for loop aspect of this, or you could make this more general by removing this criteria, I believe. And then x, we're loading x again, tl.load x pointer plus calls. That should be your homework, actually. We should leave this forward pass as a very silly forward pass and say, hey, either make this faster or make it more general, one or the other. That would be, I think, a good use, a good little homework assignment, since after all, you should definitely build something to confirm your understanding. Because if you just watch these videos, I guarantee you're not going to understand unless you go out and build something, and improving this forward pass or writing a benchmark for it and then improving it would be a good way to do so, because right now it is a bit overly cumbersome and unnecessary. tl.where calls less than n x minus mean 0. I'm not sure if we've done it in previous lessons where whenever we mask, right? So we're masking whenever our block size moves out of range of our actual embedding dimension n, and whenever we do mask those values get set to 0. You have to keep in mind, sometimes you only have to mask at the reads and writes, the tl.load and the tl.store, but sometimes to make sure your values are correct, you actually have to mask on the flops themselves, right? When you're going to do that, what you do is you do tl.where, and you say, put your mask in there, and then you do your actual calculation wherever the mask is true, and your default value wherever it's false. You have to think about what you want it to be in a given place, right? So up here with this flop, it didn't matter because when you sum up zeros and you sum up zeros in here, they just don't affect anything, so who cares? But here, for example, we just made this. It's our difference, so x minus mean. This 0 minus this mean would actually be negative mean on those masked out entries, right? And we don't want those masked out entries to mess up our accumulated values. Diff times diff. We are building a variance right now. And so to avoid that, we actually masked out those values and said, I don't want a negative mean here. I don't want a 0 minus mean here. What I want is an actual 0 still. And then it doesn't break anything when we go here because 0 times 0 is 0. And we can add those. And finally, our variance is we just sum the accumulation matrix along the only axis it has, and we divide by n. And then to make it into reciprocal standard deviation, reciprocal means 1 divided by, standard deviation is just the square root of variance, and don't forget an epsilon, because you don't want to end up dividing by 0, right? And then we can save the mean and the RSTD for later. Here, this is actually a single value, right? Because ACC was of shape block size, and after summing, it is just a single integer. So we went shape block size got converted to just a shape 1. We can actually store a single point in memory. Here's the mean pointer. We just add the row, the PID, and this mean is a single value. And then same thing with RSTD. We're going to save those for later use in our backward pass. There is the actual on purpose lesson of the forward pass, is how to save something for the backward pass later, right? Then we can say for offset. This is the same for loop deal where it seems like our for loop is more general than we originally thought it would be based off of our less than 64 kilobyte criteria. Range 0 n block size, and we say calls, same thing as earlier. So you could really speed this whole thing up by removing the for loop aspect of it, right? and not having to define calls over and over again if you were willing to stick with that whole limitation of feature length less than 64 kilobytes. Mask equals calls less than n, and we load our weights. W equals tl.load w pointer plus calls mask equals mask, and then bias should be the exact same, and actually x should be the same too, right? Because we already moved x to the correct pointer up in the beginning of the kernel. And then this is all entry-wise operations, so no need to actually specify what other is. Other will be equal to none by default, and these are all entry-wise. X normed equals x minus mean times RSTD. X is of length block size, right? Mean and RSTD are single values, so x normed is also of length block size. Then y equals x normed times w plus b, all entry-wise operations of the exact same length block size arrays, and then store that, right? Plus calls, and y mask equals mask. That's the forward pass. A bit more complicated than it should be because we actually wrote it to be general across if you wanted to parallelize, not parallelize, if you want to do a for loop within the actual embedding dimension within n, right? Even though we have this assertion out here that prevents that from ever happening. So these for loops only ever have one iteration. We could just remove this. Actually, I kind of feel like removing it, honestly. I think it's a bit silly. Hopefully that doesn't break things later. Hopefully I'm understanding everything. If I'm not, I'm going to have to re-record a lot of this stuff. It's going to suck. But this is what you do to yourself when you make code weeks before recording a video and forget what you actually did, right? Sometimes it'd be like that. Now, let's work on the backward pass, right? So our backward, gonna have two inputs. Again, it'll have the CTX object, and then it'll have DLDY. What we do here is first we can grab data from that CTX object, ctx.save tensors, and then let's go ahead and grab our shape again, same line as last time. And then we pre-allocate our output gradients, dl dx equals torch.empty, like dl dy. We could also just have put an x here instead, who really cares? And then for dl dw and b, it's a empty. This is really the same shape. Honestly, why am I not doing an empty like here? You never want to change your code last second live during an actual recording, but this is so silly. It's definitely just the same thing. And same thing for bias. I might eat my words with that later. Now, I suppose we should get into, before we start defining things, the actual parallelization scheme and the issue, right? So remember, x's shape is what? M comma n. And the shape of w and b, oh, this is a typo. Shape of w and b is of just shape n. They're a single embedding dimension vector versus a bunch of rows of embedding dimension vectors, right? What we have to do here is we have dl dy is the same shape as dl dx, right? Is we're going to have, if we were to do what we did last time with the forward pass, if we were to parallelize across the rows, across M, then every single PID would have a tiny little contribution that needs to go into DL, DW, and B, right? What's going to happen is every one of the M number of PIDs is going to have a vector of length n that it needs to contribute to DL, DW, and B. Problem being, okay, but our PIDs are all separate instances of our kernel, most of which are on separate SMs. Maybe we have multiple PIDs per SM, multiple programs per SM, but like they're all separate, right? And then DLDW and DLDB are these empty tensors sitting on DRAM. So what you might do is you say, okay, well, can we just like use tl.store and just store all the data there? Well, no. When we do our when we do a store, we overwrite whatever data is already there, right? So all of the PIDs that have an individual row that needs to be, when I say contribution, what I mean is they'll only be added up. So like there are M PIDs, they each have a row or a vector of length n that is just a contribution to DLDW and B. And the way it contributes is we need to get all of them and just sum them, right? To collapse them down to one single vector of length n, right? But so we can't just store that, like, you can't just use a tl.store because that overwrites any prior data. So if PID0 does a tl.store, it'll overwrite the empty, and that's fine. But then if PID1 does a tl.store, that'll overwrite whatever PID0 did, right? We can't actually use a store. We could load DLDW, right? Add it to whatever our PID has, its the little PID's little contribution, and then store that back, right? But now suddenly we are telling a bunch of different PIDs to read, calculate, and write, and we have no real way of knowing, wait a minute, what if our PIDs are slightly out of sync? There's no way to actually enforce an order, right? Because shouldn't PID 0 do a read, and then PID 1 do a read, then PID 2, or even some randomness in there, could be PID 0, then 2, then 1, whatever? How do we prevent them from all overwriting each other and whatnot, right? So let me actually get to the iPad to better display this. So imagine you are one of the M number of PIDs, right? And you've already stored DLDX just fine. Don't worry, that's the easy part. You have this row that you call DLDW cont for contribution, right? And so there's one for PID 0, one for PID 1, 2, 3, ... Every single one of these has a contribution. Every single one, right? They all have a contribution, and it is of shape n, right? Whereas the final actual DLDW is of shape n. What we need is to take all of these and sum them up, but they currently exist in different PIDs, which themselves might be on different SMs, right? Like SM1, or I guess you would do 0 indexing SM0, SM1, SM ... right? We need a way for the PIDs to share this information, because the actual DLDW is just some pointer, some place in memory in DRAM, right? It's some just little slice of memory in DRAM. What if PID 0 put a little lock, it's a lock symbol, I guess, I don't know. Yeah, that's a lock. A lock on DLDW. It did a TL dot, is it read? Do we use the command read, or I know store, right? Or is it load? It's load, sorry. Did a TL dot load, did its addition, it took whatever was already in there and it added its contribution, right? It did its addition, and then a TL dot store, and then an unlock. That's what we're going to do here, basically, is we're going to give all the PIDs a way to communicate by locking DLDW, the actual primary DLDW, locking its use of memory and saying nobody else can use this right now, right? But here's the thing. We could have thousands of actual PIDs. If we have to do this sequentially, if we have to do PID 0 first, then PID 1, then PID 2, then PID 3, and each one has to do a memory read, right? And a memory write as well with a flop in between. This is going to be crazy slow if they're all just waiting in line. That's a nightmare, right? What we do instead is, let's imagine we have a total of 4 different PIDs, right? 0, 1, 2, and 3. And they each have this DLDW contribution that they want to actually add together with each other. If they could, they would add all of these together real easily and we'd all be happy, right? And we don't want to wait to do our lock with 0, then 1, then 2, then 3 all in a row, right? Because then that takes 4 times as long as if just one, as if they were all to do a thing in parallel, right? We want parallel things. The name of the game in GPUs is parallel, right? What we do is we create an intermediary tensor, DLDW intermediates, right? This is going to be, let me clarify that these are on SRAM and PIDs, right? We create an intermediary tensor that is going to be on DRAM, and it is going to be, for example, let's say half the size. It is the same length n, but instead of being 4 rows, it is just 2 rows, right? What we can do is we can actually say, hey, let's have PIDs 0 and 1 contribute to this first row, and PIDs 2 and 3 do the second row, right? And so now we actually do with our locking mechanism, 0 is going to put a lock on this first row. It's going to do all of its math. Then it's going to unlock, right? We'll do that's PID 0. And then PID 1 can put a lock on this first row, do its math, and unlock it, right? So that's a sequential order of 2. And same thing with 2 and 3 over here, is they'll do their lock unlock thing sequentially. So we went from previously having to do 4 in a row, having to say, okay, first 0 gets to do its locking thing, then waiting its turn, 1 gets to go, then waiting its turn, 2 gets to go, then waiting turn, 3 gets to go. Now instead what we have is 0 and 2 go simultaneously, 1 and 3 are waiting their turn, 1, 0, and 2 are done, then 1 and 3 get to go in parallel, right? And so now we call this split of 2. This is going to be our group size, right? Forget my capital R. And so, and you can imagine if we actually don't have 3, if we actually have like like a lot of these, right? And if our group size is some number like, I don't know, 256, now we actually effectively, whereas we previously would have had to do n sequential memory reads and writes, now we can do n divided by 256 reads and memory writes. The same way we were doing 4 here earlier. 4 divided by 2 is 2. So originally we had 4 reads and writes sequentially. Now we had only 2, where 2 pairs of 2 in a parallel, right? We can do this and we can say, okay, now the intermediary tensor, great. But now that we have this intermediary tensor and it is sitting here in DRAM, right? Well, how do we do the last mile? How do we combine all of these? Well, now what we do is we say, let's actually call an entirely separate second kernel, a new one, completely like the previous kernel finished, it's all done. New kernel begins. This kernel parallelizes rather than across rows, like 1 PID for row. This kernel will cut things up by blocks within the embedding dimension, right? And each of these will just sum the chunk along n that it gets down to one single part of its row. And what you end up with is your final DLDW, right? So this is a case where we had not duplicate info, we had info across a bunch of different PIDs that we needed to sync up. And we needed to do so in a way to make sure that they weren't interfering with each other, because we had thousands of vectors that all needed to get summed together, where each vector was in a different PID, and they each wanted to sum into the exact same single vector in memory, right? And we have now made a way to do that somewhat efficiently by saying, hey, actually, instead of you all, like all n of you, waiting your turn, let's instead do a thing where we split you into groups and have you do a partial of like a portion of the sum in your little groups, right? And write that to DRAM. And then once that is done, we go ahead and we parallelize within the actual embedding dimension, right? And we say, okay, just sum vertically now. We could have, if you want to think about it, we could have actually just written all of these to DRAM and done this whole parallelization scheme across the entire matrix, across the entire non-group size, non like combined thing. But then we're using up a lot of DRAM, right? That would require using up all n rows of vectors in DRAM. So that would be in, what's that in, n by, I shouldn't have used n here. I should have used, that was my mistake. This should have been an m, my bad. This should have been an m, I apologize. And so same thing here. That's probably pretty confusing. M. Uh-oh. That should have been an M, right? Instead of using, we could have, instead of combining groups of these M rows into a couple fewer vectors, which would be, this is M divided by 256, aka group size, right? We could have instead just saved this entire thing to DRAM off the get-go and then use this scheme to parallelize it, but that would have required saving an M, N tensor to DRAM, right? Whereas what we're doing with this initial plunge of the group size thing is we are only saving an M divided by group size matrix, or by N matrix, to DRAM. So it's a trade-off right here. It's like what is your trade-off kind of thing? Do you have plenty of free DRAM? I kind of doubt it. Right? But at the same time, the less DRAM you take up, meaning the larger group size you have to do, right? Which means in the larger group size you do, it means, like, this is a group size of 2 right here was this example, right? It was 2. A larger group size means more sequentialness, because every single PID within a group has to wait in line in the context of that group is the issue. Does that make sense? I really hope so. Hopefully it'll be a bit clearer when we get to actually coding it. So what we're going to do is we're going to define our group size as 64 just off the get-go. And then a little heuristic here is, depending on how big the embedding dimension is, let's change it. So if the embedding dimension is really big, we'll keep it as 64, right? But if the embedding dimension is pretty damn small, let's do a bigger group size, right? This is just a trade-off, trading off the actual RAM per flops and whatever, and using the embedding dimension as an indicator of how much like your RAM is in general. But this isn't even like the only way to do a heuristic in this case. You could choose some other alternative method. We're going to stick with this right now. Doesn't really matter too much. But then how we also have to pre-allocate, of course, those tensors that are going to get our intermediates, right? So let's say DLDW intermediates, I'll call it, is torch.zeros, group size rows, and N for its columns. Don't ask me why I did a different device and D-type tensor. It doesn't really matter, I don't think. DLDB is the exact same thing, right? So now we have these intermediates that we're going to store all of those intermediate needed to be some values in a DRAM. But how do we build a lock, right? We had that idea of locking earlier to make sure that PID 1 waited for PID 0 to finish. What we do is we create an actual tensor for it. Locks equals torch.zeros 2 times group size. For now, ignore the 2. Pretend it's just of shape group size, right? Pretend it's just like a length group size entries, right? And it'll be int 32 because we're just going to store zeros and 1 there. I think it was 0 for unlocked and 1 for locked, I believe. And then device equals w.device, same device, who cares? For now, ignore the times 2. We'll see how that gets used later. But just imagine every entry corresponds to that group. And it says, okay, the first entry in locks means for every PID in the zeroth group, if it's a 1, wait. If it's a 0, go ahead, take your turn type thing, right? That will be, it is locking its respective row of these tensors, right? So just ignore this for a second. Every entry in here corresponds to a row in these two, and a 0 means the row of these two is not being used by any other tensor, by any other PID, I mean. Go ahead and go for it. And a 1 in any entry here means that the corresponding row in these two is currently being used by another PID, another program. Therefore, you gotta wait, right? We'll figure out the times 2 thing later as how we use that. And then we have our first kernel, Layernorm backward DLDX. We call it that because this first kernel does compute a totally finished DLDX. It, however, also computes the intermediary, the it also computes these two, right? And then the second kernel will be called Layernorm backward DLDW DLDB because it computes the actual final versions of those. And our launch grid for the first one is just our rows, and we'll call it, or we'll input X, DLDX, DLDY, weights, not biases, though we don't actually need biases because the gradient for biases is simpler. And then DLDW intermediate, DLDB intermediate, RSTD, locks, stride of X. Again, this could be a -2, I think would be fine as well. And -2 might be more general, I believe. I could be wrong though. Top of my head. Group size equals group size. Block size n equals ctx dot block size. And number of warps equals ctx dot number of warps. Right, and then for that second kernel, remember how I said we're parallelizing within that embedding dimension within n? So we're going to say grid equals lambda meta parameters Triton dot cdiv n divided by meta block size n, and then we use that grid. Now we say DLDW inner, DLDB inner, DLDW, and DLDB, the actual final ones. And then we're going to figure out what this is later, minimum of group size and of m, and then the n value, and heuristic, block size m. We are going to make for loops that move down the actual groups, right? Block size m equals 32, so even if we're at that smallest group size, we're going to split that group size in half and kind of like for loop down it. We'll see that in a bit. And block size n equals, let's say 128, rather than reusing the prior block size, which was always bigger than the actual embedding dimension vector, than the actual n. Here we're going to use a much smaller one because we're going to parallelize across this. It's very important. I went to the bathroom. Where were we? I believe about to write. Oh, not quite. We're not quite done with the backward wrapper, right? So then to finish off this backward pass wrapper, we are going to return our values DLDX, none, DLDW, DLDB, none. This is different, right? So why are there nuns here? It's because these outputs have to correspond to the inputs of the forward pass, right? And the forward pass inputs, only X, weight, and bias have gradients. The normalized shape, we didn't actually use this, and the epsilon don't have gradients, right? So keeping the same ordering, PyTorch knows which is which based off your ordering is why we do that. And if one doesn't require a gradient, you put a none there. All right, and then to finish that off and turn this class Layernorm into a form that's recognizable, we do Layernorm equals Layernorm dot apply, and from now on we can call this as a function, as we did over here. We acted like it was a function, right? That's what does that. Just a renaming to make it easier to use. And now let's get to these backward kernels. First up being that one that does the entirety of DLDX as well as our intermediate pieces, right? So we say X pointer, DLDX pointer, DLDY pointer. Notice how we actually, wait, never mind, keep going. And then our W pointer, and then DLDW inner pointer, and DLDB inter pointer. Wish there was a quicker name for those. As well as our mean and RSTD, and our locks, then that stride value, and n. We get our group size and our block size, right? So starting off, grab our PID, and then we can, our columns values, TL.arange 0, block size n, which as the forward pass, in this case, this is still longer than n. It's the next power of 2 above n based off our assertions earlier. And we can make a mask of calls less than n. And we can move our pointers of x dl dx and dl dy plus equal PID times the actual stride to get us to the correct place in those, the correct row of those, I suppose. And then we can load data into SRAM. We're going to do pretty much all at once. So let's make a little skeleton here, TL dot load something pointer. We're going to fill in values later, plus calls, mask equals mask, other equals 0, dot 2, TL dot float 32. We're going to copy this 3 times. Not sure why, but there's no other in the third one. And we fill them in with x equals, dl dy equals, and w equals. Right, and then same thing for mean and RSTD. This is just equal to TL dot load mean pointer plus PID, and then change the bottom one to RSTD. We now have the values we need. And as I said earlier, this tutorial series is not about gradients or calculus or anything, so I'm gonna speed through that piece. I will say masking here, always pay attention to what masking you need. This just normalizes. Let me make sure to mask, because you don't want a minus mean on those extra masked out values. And then dy dx, derivative of y with respect to derivative of x normed, is equal to TL dot where mask w times dl dy. Don't ask me about derivatives. If you need a derivative guide, go ask ChatGPT to walk you through step-by-step derivative of Layernorm. C1 and C2 are just labels. They are not meaningful. C doesn't mean anything. They're just intermediary pieces. TL.sum x normed times dy dx normed. Axis is 0 and divide by n, so we're meaning those two. Similar thing here, dy dx normed. Axis 0, n, oops. And finally, dl dx is equal to dy dx normed minus x normed times c1 plus c2 times RSTD. So we're not going to go over derivatives here, but that should be our prereq for this course. And once we have our dl dx, we can store that. So that's the easy part of this kernel, of the first kernel. Now the less easy part, right? So we say dl dw inner, and the row, or so the, what did I call this in the iPad app earlier? Is I called it dl dw contribution, right? Contribution, I think, is probably good. Let's go with that again. Contribution equals dl dy times x normed dot 2 w dot d type. I don't think that really matters, the d type thing, I don't think, unless it actually, if w is float 16, then it will matter, but whatever. And then dl dw as in contribution, right? And this is dl dy dot 2 w dot d type. Now, and for all the PIDs, they all have one of these, right? And these are not the final DLDWs. Sorry, this is a B right here. These aren't the final derivatives. These are just a row of which every single PID's respective row, they need to all get summed together, is the thing. And we're having trouble doing that, right? So what we do is we say, let's use the locks now, right? So our lock ID is just our PID modulo our group size, right? As in no remainder. This we get our actual group that we're in. And all of the PIDs in our group are going to take their contribution and do something with it. So we're going to remove our locks pointer plus equal lock ID to get to the correct lock. This is just a single integer entry in that locks tensor, right? It's just, right now it's a 0 when it starts anyways. And then we say dldw cont pointers. So this points to, well, wait, no, that's not what I was supposed to say. It's, what do you call this? I was calling it inter, right? dldw inter pointers, right, is DLDW inter pointer, the actual single first entry in that matrix, right? Plus lock ID times n is going to be our stride plus columns to get an actual full array. And then B, same thing. So we now know where the actual place we're supposed to take our contribution and add it into is. This is the place we're supposed to add it into, right? That's the location of that place. And then we say, all right, while this is a new function, tl.atomic cas locks pointer 0, 1 equals 1 pass. Now what this does is it says we are going to be looking at the location locks pointer in memory. It's just a single integer value that starts off at 0 and might be a 1, right? 0 if unlocked, 1 if locked, I believe, right? We say if it's 0 unlocked, right? So if we're the first PID to get here, or if we get here right after PID and it's been unlocked for us, we change it to 1, right? So we lock it. We lock it, right? And return this function, return 0, right? Which evaluates to false and therefore lets us leave this loop. Evaluates to false, so we leave the while loop, right? Whereas if it's 1, if it looks at that memory location, that little pointer, and it sees a 1 locked, right? We leave it as a 1 and return a 1, which evaluates to true. So we stay in the loop, right? We go into the loop and it says pass, and then we just have to check again. Like, can we just go back and forth until it gets unlocked by whatever PID is currently using it. So then we say we have our DLDW contribution, right? And we add it, where we add to it, we load whatever's already there in DLDW intermediate tensor pointers. I'm actually not fond of the ordering of this, honestly, but right. I suppose though, what's important to do here, the reason why I put these pointers here and I just place them right here, whereas usually I would do like pointers separate from offsets, right? Is because we want to be on this atomic lock for as little time as possible, right? I'm not sure this is like quite correct, or this is actually how this works, but I believe by making sure we do any calculations that we possibly can ahead of time, we can avoid, we can keep our time with this PID locking the lock as little as possible, and therefore hopefully speed things up, right? And then mask equals mask, and then we do the same thing for DLDB, right? And then we can do a TL.store, DLDW inter pointers. We store those same place. What do we store? We store the DLDW contribution, which is now more than just the original contribution. Now it's its contribution plus all prior contributions, right? DLDW cont mask equals mask, right? And then same thing for biases. And then once we have finished our job, like this PID has finished its job, we can say tl.atomic exchange, and we look at the place in memory locks pointer, and we can just set it to 0. Just a single command to set a single entry in DRAM to 0, right? Beautiful. Now, this could be a tiny bit better. Remember earlier when I said that the locks tensor, where was that? Locks tensor actually has not just group size entries. We're currently using the first group size entries. It actually has 2 times group size entries. We're going to use the second set of entries, the second group size length vector in there, right? The entries in there. And where were we? We are going to use that second size as we're going to call it a count. Count pointer equals locks pointer plus group size. So this moves our pointer down to the second set of group size entries, but it's the same analogous pointer in that second group. And then what we do is we say, instead of just always doing this, you say, wait a minute, on the first scenario, on the first PID to get there, to actually lock the thing and to arrive here, the first PID doesn't actually have to do a memory load here and then add. The first PID could just take its own contribution and just store it immediately, right? So we say count equals tl.load count pointer, right, which is a single entry, and we say if count equals 0, then tl.atomic exchange count pointer, we set it to 1, right? And we're basically, this is saying at 0, it's because it starts off at 0, right? It's initialized as 0. 0 means no PID has ever used this lock before. 1 means actually a PID has used this lock before, right? So then we say else, so in the case where this was the case where no PID used the lock before, now we're going to say in the case where a PID has been here before, then we do calculation, right? But if no PID has been here before, we actually can just skip these lines and go straight to storing. But if a PID has been here before, if we're in the else clause, then we do our actual math and store, right? That's it. That's the difference between counts. I was tempted for simplicity's sake to not include the count thing, but I believe it is a non-negligible speed up. I could be wrong though. It was in the original Triton documentation. I didn't bother to do an ablation test or anything, but hopefully it's an actual speed up. So then, great. Now this process still has some sequentialness to it, like whatever group size is, like that many PIDs in a row have to wait on each other, but we don't have to have all M PIDs wait on each other, right? And so we can say, cool, so now the intermediate tensors, where were they? Are filled up with entries that now themselves need to get summed together, right? So we just finished that first kernel. We can now go to our second kernel that has a different parallelization scheme. And we say at triton.jit def layernorm backward dldw dldb. Our inputs are dldw inner pointer, dldb intermediary pointer, and then final dldw pointer and final dldb pointer. Then our group size and n and block size m is a compile time variable. Block size n also compile time. This group size, is that the one that was kind of a min-max whatever? We go back to the wrapper. Yeah, so we took the min between group size and the total number of rows. I suppose M could have been smaller than group size, but that's kind of silly, honestly. I think this could have just been group size. We could have ignored this, but whatever. Don't want to change too much code in the moments. Don't want to mess things up. And this was a kind of a silly kernel. This is not the one I put so much time on. Most of my time was spent on flash attention, making sure that was very, very clear. That's been most of the work. So moving on, let's write this second kernel, right? We're calling a second kernel whose job is to take that intermediary tensor and to compress that down. So our PID and then column pointers is PID times block size n plus tl.arange 0 block size n. I don't like calling it column pointers. I prefer calling it offsets. That's kind of, pointers is gross. Then we say you're going to do an actual accumulation thing, right? So dldw accumulates, and same thing with b is tl.zeros block size m block size n, d type equals tl.float32. And so same thing for b, right? So block size m, right? We're saying m is like m is our rows, right? But we're parallelizing like within our group size and within our embedding dimension, right? So our for loop, for I in range 0 group size block size m. Bless me. So notice here, right? We have our program IDs, which were defined by block size n, right? And so each PID works in a different horizontal chunk, right, of the like embedding dimension. Whereas block size m refers to chunks down the rows, right? So we're going to do for loop. Our for loop moves down the rows of our intermediary DL, DW, whatever tensors. So row offsets is I plus TL.arange 0, block size M. Mask is, so we have a two-dimensional mask, right? First one is row pointers less than group size. I'm realizing I'm listening to an album that has a lot of crazy titles. Sorry if you're offended by Lamborghini Girls' song titles, but whatever. And then actually it's offsets, not pointers. Offsets, right? I called it offsets. Call offsets. None is less than n. And then our offsets are equal to row offsets times n plus call offsets none, right? That's our final offsets. Weird. And then we say we're going to load those partial sums and add them to our accumulation tensor, right? So we say our matrix dldw accumulates plus equals TL.load dldw enter pointer plus offsets, mask is mask, and other equals 0 point. And same thing with B. And then we sum that further. Let's call it dldw chunk equals TL.sum dldw accumulator axis equals 0, meaning we're summing along the rows, right, to get a final chunk of just block size n, shape block size n. And we do the same exact thing, for B, for biases, and then we TL.store dl pointer plus column offsets, right? And then dl chunk, so it's just a chunk of the final. Mask equals column offsets less than n. Same thing for biases. All right, that should be good. I'm sure there's crazy amounts of typos in here. No doubt. Let's go grab our test. So the floating point stuff did matter because we are going to do a test in FP16 right here. And this is a weird shape, so our masking better come into effect. And let's say Python. Wait, no, I'm in the wrong folder. CD. We've got a first typo here, is I called something some accumulator. That was over in the mean calculation. And it looks like our forward pass worked. It matched up. Then we have an error in our backward pass. Looks like I forgot to include the mean in the first call of the first kernel of our backward pass. Apologies. So that looks like this now. Oh, and I have by accident a bunch of commas in here. This is in the first backward pass kernel where we load everything. Some unnecessary commas. And also first backward pass, I accidentally did a lowercase group size, so I didn't recognize what it was. And in the second backward pass, I forgot a comma on one of my expandims here for the offsets. And then in the test, I had a lowercase l in my DLDX Triton, which didn't get recognized correctly. And there we go, passed forward and passed backward. Now let's make the actual benchmark. We are only going to benchmark the backward pass. The forward, as I said earlier, was kind of a weird forward pass. I didn't really do much with it based off the already janky version that came off of the official Triton docs. Homework assignment, go make that a bit cleaner and clearer as to what it does, preferably. Maybe I'll fix it in the actual written version of the website. Check out for that if I fix that. I might do that. I probably should. .testing, .performance reports, right? And so Triton, .testing, .benchmark, x names equals n is the important one, right? That we're going to test different values of. X vals equals 512 times I for I in range 2 to 32. Line args equals provider. Line vals equals Triton torch. Line names equals Triton PyTorch, right? Styles, I'm too lazy to, it's just matplotlib styles, as always. And then we're gonna measure in gigabytes per second, and our plot name and args. We don't actually use this. I don't think there's a reason to be putting M here, I don't think. And then D type. Yeah, and in the in the flash attention kernel, the next lesson, we're gonna actually use args, and we seem to have used them here, but I think really this is a holdover from when I simplified the code. I don't think these need to be here at all. I'm pretty sure these can just not be here, I think. Um, they might have default value something. No, they should be pretty useless. These, I think you could just delete those, and things should still all work, I believe. In the flash attention next lesson, we'll actually take advantage of args to its fullest extent. But for now, no. Benchmark, I believe that this stuff is just useless. I think that's unnecessary. But so benchmark m n d type provider mode equals backward eps equals 1e negative 5. Maybe you can't delete them. This might be using float 16 as a default value for d type, which is not what it's meant for, really. You should be putting in multiple values for this kind of thing, which we'll do in forward in the flash attention again, but whatever. And then device equals device. I'm supposed to be using args for like different conditions of like how many benchmarks you want to run. Each one's a bit different in some way, but we did not do that. Now, x shape, let me just actually say x equals negative 2.3. We can copy these from the test, I believe, right? Yeah, we can just copy those from the test, and then we can say quantiles. We're gonna go median, and then a 10% confidence interval, and defining our function of y forward. This is a different way to do it. It doesn't really matter, honestly. If provider equals Triton, return Layernorm. That's our Triton wrapper. X, what's W shape? It's N, right? Weight, bias, epsilon. And if provider equals torch, return torch.nn.functional.layer.norm xw, wait, no, this is n tuple, right? Weight, bias, epsilon. That should be good there. Then if mode is forward versus if mode is backward, we don't actually test the benchmark the forward pass here. So this is kind of silly. That's kind of silly. I'm gonna on the live edit this. I think I at one point did have a forward pass. What's it called? A forward pass. A forward pass. What's it called? Benchmark. But that's gone now. I believe these are a lambda, right? You know what? I'm gonna keep it as similar as I had it, just to make sure I don't mess anything up and minimize weirdness. But so we do y equals y forward. That's a silly thing to do there, but whatever. And then gigabytes per second is lambda ms 3 times x dot numal. You can ignore the smaller tensors, given big annotation and whatnot. Size. So those should correspond to, I guess that would be x dldx and dldy is the 3, like, and then they each have these number of entries in this element size, right? X dot element size times 1e negative 9 divided by ms 1e negative 3, right? And then ms min ms max ms is triton.testing.do bench. lambda y dot backward dldy. Do I have a dldy anywhere here? I don't, it seems. So dldy equals 0.1 times torch.random like x. So we're inputting that. Obtain graph equals true. Let's this is the first entry. Quantiles equals quantiles. Grad to none x. So I guess it's actually capable of doing its own gradient setting to 0. And then I guess we're gonna do 500 repetitions. Wow, those are some new arguments for us. And then we can return gigabytes per second ms, gigabytes per second min ms. Wait, no, max first. I hate how the ordering is different. Why would two different Triton functions expect and return different orderings for the ms? And gigabytes per second min ms, right? Hopefully that works. And let's go ahead and copy this. What are the odds? So we're in the same thing, but with a dash dash benchmark, right? We forgot line name comment here. This is a singular, not args. And I have not installed everything. Silly me. Let me install real quick. Pip install pandas. And then that should be good. And the benchmark should now be running. Can we get NVIDIA SMI up and visible? Watch-N1 NVIDIA SMI. Utilization pretty high. And boom, mistypes, but look at that. The backward pass only being benchmarked. Triton being much faster than the default PyTorch version, right? I think is this our first kernel that's actually faster? I can't remember exactly. And honestly, it could be sped up. It was the forward pass anyways. I know we didn't test that, but that one was a little bit of a nightmare. But good stuff right here. We didn't even auto-tune anything. This is all heuristics, right? This is all heuristic value set. Imagine if you actually auto-tune some stuff. You can get pretty fast with this, which is very, very cool. But that is it for today. I'll catch y'all in the next video on the flash attention kernel, which is, if I do say so myself, I think it should be a much better video than this one. This one, I didn't look at the actual code or anything for this for a couple weeks since actually writing all of it and everything. And it's a bit less organized, but the flash attention one had a lot more work put into it. So hopefully that one will be good, and I will catch you all then. End of video.